Good morning. Welcome back to looking at data structures with CS2420. We're going to look at the idea of how we can actually measure the effectiveness or the efficiency of the code we're looking at. So we can start seeing about how effective, it is to use different types of methods to actually see how efficient they are for doing different types of stuff, what kind of logic we can actually do to try and have using one type of a method versus another type. And we're going to start by looking at this by using our doubly linked list. And we're going to look at the DoubleList, which is the implementation of that abstract data type of doubly linked list that we already have designed in some previous videos that we've looked at. And so we're going to use that idea to actually, or use that structure actually, to look at the idea of what it takes to add using an add method versus an addFast method. So we can look at some ways that we can actually, simply by using the knowledge we have about the structure, to have a more efficient use of the structure itself. And so what we're going to look at is we're going to look at the actual code for the timing on that. Then we're going to go look over the actual methods themselves we're using to get access to that. So we can look in about how the actual data structure itself is put together and how we can actually make that more effective. And again, why sometimes linear data is not usually the best way to actually store stuff when you're trying to do things fast. So here we have our test list timing method. It's inside our structure controller. And as you can see, I've created a double list of type int. We can use this to store anything, of course, but since int is really easy and we can just make it right away, we'll go ahead and do that. And then make a timer object to start the total time, so we can actually measure the total time it takes to do this. And then we have a loop that we're going to go through from 0 to 10,000. Since doing something with simply 1, 10, 5, 30, those are really small. Computers take 0 time to execute those really small numbers. And so we'll start looking at using a much larger scale. So we'll start with 10,000, and we'll change that number and actually go a little bit higher and see what kind of impact it's going to have for that. So we'll make 10,000 random numbers and add that to a data structure. So that's actually a fairly large quantity of information for a human to actually deal with. So we've got that there. And so we'll use another random number, just add random, which will get some random integer and put it in there. We're going to make two different arrays of long, slow time and fast time. They're both 1,000 big, so we can actually keep track of that information. And then initialize two double variables, average slow and average fast, to be 0.0, so we can keep track of the information that goes along with that. And then we're going to do 1,000 retrievals. Now we're not going to do anything with the retrieval, simply going to actually see how long it takes to do that. And so we're going to repeat this 1,000 times, and we're going to get some random index somewhere between 0 and 10,000, so we can actually just get somewhere in that data structure that we have. And we're going to use start timer, and we use the getFromIndex method at that random index and stop it once we've retrieved that. And so we have start and stop so we can get that time right there. We're then going to set that time in microseconds and store it in the slow time at that index. Again, starting at 0, 1, 2, 3, 4, 5, up to 9,999. And repeat that same process again, but using the getFromIndexFast method. Our faster way of manipulating that bidirectional node-based structure, so we can actually go from a faster way of actually finding that information. And then we'll store that time inside its index at that spot of the array as well. And then again, reset the timer, always reset it because we want to actually make sure we have the correct value on that. Bizarre, I know. And then because we it's going to happen at the same time, we'll store the average slow plus equals slow time subindex and average fast plus equals fast time subindex because we're going to have that information anyway. So we've got that fast time index we're going to be looking at, and then we have our average slow is going to equal average slow divided by 1,000. So we want to actually take that value and get an average for it. So we take the total we have divided by the number of slots. Hey, regular average information. And then our double savings is going to be average slow minus average fast. Now, there is no guarantee we're going to have the biggest possible value in that because of the fact that we're just simply getting the averages and subtracting them. It could be that the average slow is actually not going to be the better time or the slower time. So that could possibly give us a negative number, and that's okay. And then we're stopping the total time to actually do all this work. So we can just see about how long it takes to do all of the work we just did. Like dealing again with 10,000 things, that seems like a lot of time. So let's take a look at that. And so we'll use our total timer display information method, which will just grab and display that information for us. And then we can get the average speed for getFromIndex in microseconds, and average speed from fast on the, in microseconds as well, which gives us the time savings of that. And so again, we're looking at how much time it takes to actually get something from some random index inside our data structure. And then we're going to go ahead and reset our value of average slow and fast back to 0. And again, start going through 1,000 times. We're going to do the same approach. But this time, instead of simply just randomly getting some value, we're going to add a value to some random index within that. So we're going to actually see which is going to be most effective. And so we have int random index is random modulo 10,000, the original size of that data structure. And we're going to add to it. So it is going to be a little bit off. That's okay. And we're going to do this 1,000 times. And then we'll get another random value just to shove inside that because we're just going to insert some random value into that. And again, the same approach, we're going to do double timer, start timer, and add an index using the regular method, passing it random index and random value, and then stop that timer and store that time in slow time. And repeat that process for using the addAtIndexFast method. Again, start and stop the timer appropriately, and then again, get that execution time to store that in there. And then again, rebuild our average as needed. We're going to go ahead and then recalculate the actual average divided by 1,000 yet again, recalculate the savings by subtracting the values, and then reprint out that information so we can actually see that. So that's what we have right there. Let's go ahead and run this really fast so we can see what kind of thing we're going to have with that. So we'll do Command R to run this. And we're going to go to test the timing of DoubleList. Execution time total is 43,143 microseconds, aka 0.04 seconds, nothing. Okay? Average speed to go through and put something in or get something from a spot took 27.04 microseconds. Oh, okay, 27 microseconds. Not too bad. Average speed with the getFromFast is 14 microseconds. So we actually have a savings, almost basically half of that. Really quite nice. So we have a pretty good savings on that for that. So it's almost 50% faster. Average speed from the addAtIndex method, 34 seconds. addAtIndexFast is only a little bit faster at 20 microseconds, a time savings of 13 microseconds for average. And again, we're looking at the average case. We're not looking at the actual fastest time because that's just a one-off. What we're looking for is overall, over all those different executions, which one's going to be the most accurate. And so we have that finished testing. Exit code 0, fantastic thing. We made sure we exited properly. So let's go take a look and see how that actually works. So I'm going to go from my controller package, go to my model, go to my linear structures, and go to my inherits from DoubleList to go to DoubleList. And we're going to take a look at what we've done. So we used to use the add method just to throw something in there, no big deal. That just dumps stuff into the structure. But what we really want to have on here is we have the idea of our getFromIndex versus our getFromIndexFast. And what we have in getFromIndex, this looks just like the getFromIndex on our array class as well as our list class, where it grabs the index, asserts that the size itself is actually valid, and that it's going to go through, loop up to that point using pointer chaining, starting at the front, going all the way up to the end, one at a time, doom, 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 ad nauseum, until it gets to the spot it wants, grabs that data, and returns that. So that's just going one direction. But because we've made the bidirectional node, so it can go this way or that way, we have potentially the ability to go faster with that. And so that's where we have our getFromIndexFast method. And we'll scroll down and take a look at that. So our getFromIndexFast method takes the index, again, asserts to make sure the index is a valid number, so we can't make something that's too small or too big to get something out of that, no big deal. Again, we create a value that can return from, make a pointer reference to that, but then we're going to do an if test. What we're going to check to see if index is less than size, we're going to check to make sure if index is less than half of the size. So the index is less than this.getSize divided by 2. So we're going to use the pointer operator, grab that, and check the size. Oh, if it's less than halfway, so if it's in the first half of our structure, we're going to start over here at the front. And we'll go up to the half, and we'll grab it right there. Otherwise, our else case, it's at the end of the list, or it's closer to the end than it is to the front. We'll start at the end, and we'll go use the previous pointer chain. So it's going to cut down the amount of times we have to look for something potentially in half every single time. And that's what we saw in almost 50% savings when we use the idea of our addAtIndexFast. And by doing so, we can see that we can have a default method that we can simply just use this automatically, so we can make it so that our code is actually more effective overall all the time. And as you can see, inside the if block, all we're doing is just grabbing front, going up for 0, 0 is less than index, and using the pointer chaining, reference equals reference selector, get next pointer, pointer chaining all the way towards that point, up till and including the spot we'd get to. If the reference or the index we're talking for right here is actually bigger than half, anytime so it's closer to the end than it is to the front, then at that point we want to go ahead and start at the end. We use our end pointer. Oh, end pointer is closer to that variable, so let's go through and we'll go backwards. We'll start position is equal to this get size minus 1. Position is greater than index, position minus minus. We'll go from the back end of the index and we'll go backwards through the list until we get to the spot we want to go. And so it's a much faster way because of the fact we only have to go half the list. We never have to search the entire list through that to get to a spot. We can merely search through half the list. And so by doing this, we cut the average amount of time attached to searching for something inside a list in half. And so the linear, it's still a factor of n. We're looking at the big O of n, it's just n over 2. So it's still a growth rate of order of n for the actual efficiency of this algorithm, but it's a much slower growth on n because it only goes n over 2. So that's definitely going to be a much slower growth rate on that. So we have a nice way we can do that. We can do that same approach on our addAtIndex versus addAtIndexFast. So we have in our addAtIndex, we have the, right here, we're just going to make a pointer for slow adder and slow next because we want to get the one we're getting to and the one that we were, that was its next. We're going to pointer chain all the way through, and we'll just start at the beginning, go dot, 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 all the way down through there. And once we get to the spot we want to, then we'll say that slow next is going to be the one that's after slow adder's next. So we can get the one it was pointing to. And then I'm going to go ahead and create a brand new node called addAdNode. And I'm going to take that new node and I'm going to use my 3-parameter constructor so I can initialize it with the value the previous pointer and its next pointer, so I can connect it automatically to the right nodes. And then because I've done that, I can go ahead and take slow outer, the one that I was at, and set its next pointer to added node. And then as long as slow next is not null pointer, aka where I'm pointing to, I'll set slow next previous's pointer to point to me. Sweet. So I've got that ready to go. So I can actually have that all pointing together, and then I'll update my size by 1, of course. No big deal. Now, the same approach we saw for the getFromIndexFast works on the the addAtIndexFast as well. So let's go ahead and take a look at that. Again, we have our index and type value, and we have, again, a separation based on index. If it's less than half the size, we'll go this way. And again, I use that same approach, make a pointer, and go up through and go front, creating it with its front and its next, and add it up and set that right there. Otherwise, I'm going to go start at the end and go to set its previous, and start at the end and go back, going backwards this way one at a time. And again, I do that same approach. I set it so it's previous and its next get added, and then I add the pointer appropriately, adding that information just in case something weird's happening. Have that null pointer check as well. And then again, I also do this selector set size to update size by 1. And so we have the ability to actually grab that information, so we can make it so it goes faster because we cut the amount of work that we have to do always in half. For the, or not always in half. We cut the amount of work that we have to do for operating on the list, potentially in half every single time, because we only have to go up to the midway point either way. We never have to go all the way through from beginning to end if we use these faster methods. And so we can actually have this as the default method and simply have that automatically in there. And so we can actually see the time savings on that by using 2 different methods and calling them on that. And so when we look at how we can do data structure design, we can make some efficiency ideas by having the ability to actually say, oh, I know these 2 points within this, I can make it so I can automatically go from there. And so by having that information automatically available to us, we can make our data design more efficient, and we can make our data structures more efficient overall. And we'll see this become much more effective as we look at the non-linear data structures, where we have more information potentially available to us, or we can have information automatically stored within that, so we can make it so we can actually have a much more effective way of storing and retrieving data. And so we can see the difference effectiveness of that. Thank you, and have a great day.